Thank you very much, Professor Spentavadia, for giving us the opportunity to host the AtHome Discovery Camp. The last part of the Discovery Camp, where the 21 astronomers, citizen scientists have been trained, the last part is this outreach-like thing, where you will be having half a day exposure to what is astronomy, what is the initial training part of citizen science that we do with giant meteor wave radio telescope. This is called AtHome Discovery Camp, but what is more important is that we move to different institutions so that local people can get exposed to this training. Unless you are a research scholar, you don't join research institutes. So I kept on moving different institutes since last 5 years. Institute of Physics, Bhubaneswar, Nehru Planetarium, Delhi, Vigyan Prasad, Delhi, Harishchandra Research Institute, Allahabad, my own institute, Center for Excellence in Basic Sciences. They keep hosting this kind of citizen science training program so that we can all participate in discovering and doing science research with giant meteor wave radio telescope, which is the largest such radio telescope in the world, 3 times bigger than the VLA. So what is more important is how all of us, through citizen science participation, which is in between something outreach, education, research, something slightly different, combination of media, education, research, we can all join in. So unless you get to know that such a platform exists, that you can do it from your home, through Facebook, through internet, through YouTube, through NASA Skyview platform, how will you participate? And GMRT is so powerful that the data is so much there that everybody has a chance to discover something that nobody else has seen before. Nobody else has seen that part of the sky. So let's, including all my friends who got trained here, let's thank ICTS for giving us the opportunity to reach to you. Thank you. Chiranjeev will take over now.
So from my side also, thanks to ICTS and Professor Spentavadia. Now our talk sessions are starting. And the first speaker is Professor Arnab Rai Choudhary. So to introduce him, he did his PhD from University of Chicago in 1985. And after that, in 1987, he joined IISc as a faculty. And he is basically a theoretical physicist whose interest lies in solar physics. And besides the solar physics, he has also interest in active galactic nuclei, jets, accretions, pulsars, etc. Also, he has interest in history of science. And he authored quite a few books, and to name them, The Physics of Fluids and Plasma, then Astrophysics for Physicists, and undergraduate students can actually read these Astrophysics for Physicists. It's very interesting books. Others are also interesting. And the third book is Nature's Third Cycle, a story of sunspots. So please go through those books if you have opportunity to buy it or if you get it in library. And he is a fellow of Indian Academy of Sciences, the National Academy of Sciences of India, and the Indian National Science Academy. And he was a recipient of Alexander von Humboldt Fellowship. And he is at present recipient of J.C. Bose Fellowship. He published number of papers. So those who are interested in science can download some of the papers because these are nowadays available in the internet. And he visited various places with visiting positions in USA, Scotland, Germany, UK, Hungary, China, Japan, etc. And he has produced 6 PhD students. So now I invite Professor Rai Choudhary to come over and deliver his talk. Thank you.
Okay. So thank you for this kind introduction, and also I thank my young friends for coming to listen to me on a Sunday afternoon. So I hope that you will find this subject sufficiently, I think, entertaining to feel that it was worthwhile. So I shall tell you about one of the most I think, intriguing natural cycles known to mankind, the so-called 11-year sunspot cycle. So probably many of you know that in certain years, lots of sunspots are seen, and then a few years later, you see very few sunspots, and then more sunspots appear. It goes up and down in a cyclic fashion of 11 years. So let me begin by showing you how the sunspot number has varied with time over the last 400 years, starting from the year 1600. So it was Galileo and some of his contemporaries who were the first scientists to study sunspots systematically and left records behind them. So initial entries just after the year 1600 are based on their records. And then surprisingly, there was a period of some 80 or 85 years when sunspots were not seen at all. And after that, you see that the sunspot number has gone up and down with a rough period of 11 years, but it's not strictly periodic. You see lots of irregularity. Some cycles have been very strong and some cycles are weaker than that. So presumably, most of you knew about this 11-year cycle even before I told you about it, but I may mention that there also seems to be some kind of a 50-year periodicity in this field. It seems that major breakthroughs in this field take place roughly at intervals of 50 years. It was a little bit more than 150 years ago when Heinrich Schwabe discovered this 11-year cycle of sunspots. He reported the discovery in 1844. Then about 100 years ago, this American astronomer George Ellery Hale took the spectrum of a large sunspot, and in which he detected Zeeman splitting, about which you must have learned in your physics courses. So from Zeeman splitting, he was able to conclude that the sunspots are regions of strong magnetic field of about 3000 Gauss. So this was a momentous discovery in the history of physics, because this is the first time somebody conclusively established the existence of magnetic fields outside the Earth's environment. And now we know that magnetic fields are ubiquitous in the astronomical universe. So they are found in stars, planets, galaxies, everywhere. And also with this discovery, it became clear that this 11-year sunspot cycle is nothing but the magnetic cycle of the sun. Then about 50 years ago, Eugene Parker formulated what is called dynamo theory, which is still the starting point for us to understand why various astronomical objects have a magnetic fields. So going by this trend, you would think that right now would be the time for another breakthrough. So that is actually the case. So in a half an hour talk, I shall not be able to discuss much about what is happening at present in this field, but hopefully we'll have a little bit of idea. So after Hale's famous discovery of magnetic field in sunspots, a decade later, Hale and his co-workers made another very important discovery. So often one sees two large sunspots side by side, like these two sunspots, and here for comparison you can see the size of the Earth. So some large sunspots can be larger than the Earth. And Hale et al. Discovered that in such situations, usually the two sunspots have opposite polarity. If one has a positive magnetic polarity, the other has a negative magnetic polarity. And the most plausible explanation for that is this, there must be a strand of magnetic field going underneath the sun's surface and maybe poking its nose through the sun's surface in this fashion. So then there will be two intersections on this sun's surface, and if these two intersections become the two sunspots with concentrated magnetic field, then in one intersection you have magnetic field lines coming out, making it a positive polarity sunspot, and in the other you have magnetic field lines going down, making it a negative polarity sunspot. So in a few minutes I shall come to the theoretical question, how such remarkable magnetic structures arise. But if there are really such magnetic structures, then we expect that the sun's corona above the surface will be full of this kind of magnetic loops. And that happens to be the case. So in the last few years, astronomers have developed marvelous techniques for imaging some of these loops. So here you can see some coronal loops. They're actually imaged in extreme ultraviolet. And Professor Jayant Murthy, just after me, will tell you something about ultraviolet astronomy. Okay, and now I show you something really remarkable, which is called a magnetogram map of the sun. So a magnetogram is something which measures the magnetic field at every point in the solar surface. And if the magnetic field is positive, then white color is put. And if it is negative, then black color is put. And if it is too weak, then gray color. So you can see in some places a white patch and a black patch side by side. So these are actually two sunspots. If you took an ordinary white light photograph, you would see two sunspots. And since one has positive polarity, it is seen as white, and another has negative polarity, seen as black. And if you look carefully, then you will see that in the northern hemisphere, this white is to the right and black is to the left. And in the southern hemisphere, it's opposite. The white is to the left and black is to the right. And it remains like that for one cycle of 11 years. And after that, it reverses. So if you took a magnetogram map 11 years earlier or 11 years later, then you would find that in the northern hemisphere, black will come to the right and white to the left. And in the southern hemisphere, also it would get reversed. And another thing you note that if you draw a straight line connecting the centers of the sunspot pairs, you will find that the straight line is nearly parallel to the sun's equator, but not exactly parallel, with a little bit of tilt. And that tilt increases with latitude. At higher latitude, sunspot pairs have larger tilt. It's often called Joy's law because it was discovered by Joy. So this is Joy's original plot of how tilt varies with latitude. Anyway, for the time being, if we forget about this tilt, then looking at this distribution of sunspots, you get a feeling that in the northern hemisphere, underneath the surface, there must be some magnetic field lines going like that. So if part of this magnetic field comes out, then on this side you will have positive polarity, on this side you will have negative polarity. And in the southern hemisphere, you will have magnetic field lines going this way to explain this occurrence of positive and negative polarity sunspots. In other words, underneath the surface, we expect the magnetic field to have this kind of structure. So in the jargon of dynamo theory, this is called a toroidal field. On the other hand, we expect that the Earth's magnetic field is somewhat like this. And this kind of magnetic field is called a poloidal field. And in this famous 1955 paper formulating dynamo theory, Parker made a remarkable suggestion that the sunspot cycle is produced by an oscillation between the toroidal field and the poloidal field. Somewhat like the oscillation between potential and kinetic energies in the simple harmonic motion with which all of you are familiar. So this was really a remarkable suggestion for that time, because at that time, astronomers didn't even know whether the sun has a poloidal field or not. And in fact, in that very year, 1955, Babcock and Babcock, a father and son pair of astronomers, first detected that the sun has a sort of a weak polar field, which is much weaker than the sunspot field. It's about 10 Gauss or 10 to the power minus 3 Tesla, whereas the sunspot fields are 0.3, much stronger, about 0.3 Tesla. Okay, so, but is there really an oscillation between this toroidal and poloidal field as Parker suggested? So that could be established only after astronomers gathered data about the sun's polar field for many years. So here I show you the relevant data, how the polar field has varied with time. So here the solid line is the north polar of magnetic field of the sun, and the dashed line is the south polar magnetic field, and below it this dotted curve is the how sunspot number has varied with time. So you remember that the sunspots formed from the toroidal field. The sunspot number is a measure of the strength of the toroidal field. So you see that the toroidal field is strongest at a time when the polar field, which is essentially the poloidal field, that is close to 0, and the polar field or poloidal field is strongest at a time when the sunspot number or the toroidal field is close to 0. So you really see a kind of an oscillation between the toroidal field and the poloidal field, exactly what was envisaged by Parker. And it's almost mind-boggling to think that a theorist could come up with such ideas many decades before this could be observationally established. Okay, so after giving this sort of an overview of some of the important observational aspects of sunspot cycle, now I can point out what I would call the central dogma of solar dynamo theory. So the sun's magnetic field consists of both a toroidal component and a poloidal component. The sunspots arise out of this toroidal magnetic field, and the polar field is a manifestation of the poloidal magnetic field. And since there is an oscillation between these two, so there has to be a process which produces toroidal field out of a poloidal field, and there also has to be an opposite process which produces poloidal field from the toroidal field, so that we get the cycle. So in this half an hour talk, I certainly cannot give you full theoretical explanations of various aspects of the central dogma, but now I shall get into theory, and I hope I can give you a little bit of idea how one provides the theoretical explanations for various aspects of central dogma. So the first question is, what are our theoretical tools and which branches of physics do we need to address this phenomena we are discussing? So in elementary school textbooks, you might have learned that matter exists in 3 states, solid, liquid, and gas. And for about a century, physicists know that there can be a 4th state of matter, the plasma state. So if you heat a gas to very high temperature, then atoms get broken up into negatively charged electrons and positively charged ions, and that is called a plasma. So it was this Indian physicist Shah who studied this process, how on increasing the temperature, an ordinary gas gets converted into a plasma. And since because of the electrical attraction between ions and electrons, they are very well mixed. So if you take a small volume element of a plasma in which there are sufficient number of electrons and ions, you would find that their electrical charges would more or less balance each other. So a small volume of plasma will be charged neutral. So does that mean that a plasma has the same properties of a neutral gas? So no, that is not the case. So difference becomes apparent if you put an electric field. So in an ordinary gas, usually the electric field will not do much, but in a plasma, if you put an electric field, then the positively charged ions will move in the direction of the electric field, and negatively charged electrons will move in the opposite direction, so making a strong current to flow. And when a current flows, you know that it will give rise to magnetic field. So there can be complicated interactions between plasmas and magnetic fields. So how does one study that? So although the air is made up of molecules, you know that for many purposes when we study the flow of air, we can treat the air as a continuum. So similarly, even though the plasma is made up of electrons and ions, for many problems, plasma can be regarded as a continuum. So the branch of plasma physics in which we treat the plasma as a continuum is known by the tongue-twisting name magnetohydrodynamics, abbreviated as MHD. So you basically put together the equations of electromagnetism and the equations of fluid mechanics to get the equations of MHD. So certainly I don't want to give you get into the details of the mathematics of the subject, but I shall mention one theorem which is extremely important in all areas of astrophysics. That is called Alfvén's theorem of flux freezing. It was developed by, formulated by Alfvén, who won the Nobel Prize for this Alfvén's theorem, and many of his other important discoveries of MHD. So even this theorem is not very difficult to prove. If I were given maybe one or 1.5 hours, then starting from basic equations, I could do step by step. I could prove this theorem. But since I don't have the time for that, maybe I shall just state the equation. So let me, these things I suppose I can rub. So let me just explain a little bit about this theorem. So suppose in a plasma you consider some surface A, B, C, some hypothetical surface made up of plasma material, and suppose there is motion in the plasma. So after some time, this fluid element here will go here. It will become A prime, and this will go here, will become say B prime. And in that way, in the whole surface, ABC will become this plasma materials, which was here, will come here. Say it was here at time t, and it comes here at time t prime. So suppose there are some magnetic fields, so there will be some magnetic flux associated with this surface. And after some time, when the surface has come here, it would again have some magnetic flux associated with it. And Alfvén's theorem tells us that the whatever was the magnetic flux associated with this surface at time t, so when the surface moves here, the same amount of magnetic flux has to be associated, provided the effect of resistivity is negligible. What do we mean by effect of resistivity being negligible? One can introduce a dimensionless number called magnetic Reynolds number, in which this resistivity rho appears at the bottom. So when resistivity effect is negligible, then this magnetic Reynolds number is very large. And you see that the magnetic Reynolds number also depends on L, the size of the system. So for large astrophysical system, this magnetic Reynolds number is very large. And when the effect of resistivity is also negligible, and then this Alfvén's theorem holds very well. But in the laboratory systems where L is much smaller, usually this flux freezing doesn't hold because the magnetic Reynolds number is much smaller. So let me illustrate this point with a thought experiment. So suppose you have a chunk of plasma between the pole pieces of a magnet, and suppose you move it aside. Then what happens? In a laboratory situation where you have magnetic Reynolds number much smaller than 1, nothing happens. This chunk comes here. But in a situation where the magnetic Reynolds number is much larger than 1, as it happens in the astrophysical situation, you know that Alfvén's theorem has to hold. So whatever magnetic flux was passing through this plasma chunk, the same magnetic flux has to pass through these. And that is possible only if magnetic field takes up this kind of a configuration. So in the high magnetic Reynolds number situation, that magnetic field behaves almost like a plastic material. I think it can be deformed or twisted, and it behaves completely differently from the way magnetic field behaves in a laboratory system. So there is a sort of a symbiotic relation between MHD and solar physics. There are many solar phenomena which require MHD for explanation. On the other hand, some of the most interesting theoretical predictions of MHD are for high magnetic Reynolds number situation, which cannot be tested in the laboratory. So we have to look for their verification in the sun. So we often say that the sun is the best laboratory for high magnetic Reynolds number MHD. So with this little bit of background of MHD and concept of flux freezing, now I can explain one aspect of this central dogma of dynamo theory, in which we need to have a generator or get a toroidal field out of a poloidal field. Let us see how that happens. So suppose initially you just had a sort of a poloidal field in the sun. And the sun also rotates around its rotation axis like the Earth, with the rotation period being 27 days. But unlike the Earth, which rotates like a solid body, in the sun, the angular velocity varies from region to region. So near the equator of the sun, a point would take about 25 days to go around the rotation axis, but near the pole, a point will take more than 30 days, something like 33 or 34 days to go around the rotation axis. So this is a type of thing is called differential rotation. So basically the region near the Earth's equator is moving faster, and then we have a situation exactly like that. This motion of the plasma, the magnetic field lines got dragged. So here also the faster moving region near the equator will drag the magnetic field line, and if you begin with a poloidal field and you would end up with a toroidal field, you can see that, and in the two hemispheres, the toroidal field has opposite signs. So if parts of this toroidal field come up to the surface, you expect that the bipolar sunspots will have opposite signs in the two hemispheres. So I started at what time, Ananda? So shall I stop at 3 o'clock by this clock? Okay. Okay, so this question is, why should parts of this toroidal field float up to the surface to produce a bipolar sunspot? So I shall just try to give you an explanation for that, and then maybe I shall stop with making some general comments. So before coming to the question, why regions will float, let me tell you what the interior of the sun is supposed to look like according to the theoretical view. So the energy of the sun is produced by nuclear reactions, mainly at the center, where the temperature is about 15 million degrees. And then there is a region up to 0.7 solar radius where energy is transported outward by a process called radiative transfer, which means that photons random walk to the solar material. Then from 0.7 solar radius to the surface, we have a region called convection zone, where energy is transported by convection. So sunspots are certainly regions of concentrated magnetic field sitting in this turbulent convection zone. So you may wonder why magnetic fields are concentrated in sunspots instead of filling up all space. So to understand that, we need to study the interaction between magnetic field and convection. So that subject is called magnetoconvection, of which the fundamental theory was established by Chandrasekhar, and then many others like Weiss worked on it. So basic idea is like this. Suppose you have a vertical magnetic field in a fluid which is heated from below. And you know that when the temperature gradient is sufficiently strong, a convection will start. But magnetic field lines have tension associated with them, so magnetic fields will try to resist convection. So convection will start only when the temperature gradient becomes sufficiently strong. And then nature finds it expedient to separate space into two kinds of regions. In some regions, like here, the magnetic field lines will be expelled and convection will take place freely. And in other regions, magnetic field lines will get bundled up like this, which are called magnetic flux tubes. And within that, convection is suppressed. And because of the suppression of convection or heat transport, what happens is that the tops of these regions will become colder compared to this region. So that's why I think sunspots are supposed to be this kind of a flux tubes which are bundled and which magnetic fields are bundled together by interaction with convection. And that's why sunspots, that's why these regions are colder and appear darker. So here is an image of sunspot. You see all this granular structure around. So these are nothing but the convection cells. So we believe that the magnetic field exists throughout the convection zone in the sort of magnetic flux tube. So now I can come to the question, why parts of this toroidal field produced by this sort of stretching of poloidal field, and why parts will float up to the surface? So first of all, where do we expect this toroidal field to be produced? So basically, you expect them to be produced where there is a variation of angular velocity, And in the last few years, astronomers realized that there is quite a lot of variation of angular velocity at the bottom of the sun's convection zone. So we believe that it is at the bottom of the convection zone that this toroidal, toroidal flux tubes exist. And you consider a sort of a horizontal flux tube, and there has to be some pressure balance between inside and outside. So outside you only have gas pressure, and inside, apart from gas pressure, magnetic field also has a pressure, which in your college physics textbooks you learn that magnetic pressure is given by B square by 2 mu. And since this is a positive quantity, this means that the pressure inside a magnetic flux tube is less than the pressure outside, and which very often, though not always, implies that the density inside is also less than the density outside. And Archimedes taught us many, many years ago that if a system in a fluid has less density compared to the surrounding, it will become buoyant. So this is called magnetic buoyancy, of which the idea was put forth by Parker, again in the same year, 1955, in which he wrote his fundamental paper on dynamo theory. And he also showed that magnetic buoyancy is particularly destabilizing within the convection zone, but it can be suppressed below the bottom of the convection zone. And as I already pointed out, these toroidal fields get produced at the bottom of the convection zone. So suppose a part is within the convection zone, whereas other parts are below the bottom. So then the part within the convection zone will become buoyant and rise and eventually to produce bipolar sunspots. So to study how I think sunspots are produced, you have to do some calculations of how part of the toroidal magnetic field from the bottom of the sun's convection zone rises. So I don't have time to go into the details. So I may mention that some of us in our group, we did some of the first important calculations on this subject and give an explanation for things like Joy's law. Anyway, I think you have got an idea of this subject that if you start from a poloidal field, how this, due to flux freezing, you can explain the production of this toroidal field, and by using the idea of magnetoconvection, you can explain why magnetic field exists in the form of flux tubes, and the idea of magnetic buoyancy explains how these bipolar sunspots form. So starting from a poloidal field, you can explain these various aspects of formation of sunspots. But where do poloidal fields come from? And if we want to have the oscillation between toroidal field and poloidal field, then from toroidal field, you have to generate the poloidal field. So that is, I would say, the heart of the dynamo theory, to explain how poloidal field comes from the toroidal field. So again, if I were giving a 1 hour talk instead of a half an hour talk, I might have tried to give a little bit introduction of that subject, but today I don't have time. But anyway, I hope that you have got some idea of the field. So let me end by mentioning about my popular science book, which was already mentioned. So in this book, I have tried to give a non-technical introduction to the subject of 11-year sunspot cycle. So this book was published by Oxford University Press in 2015. So when it came out in hardback, priced as 25 pounds, I was worried that nobody will buy a popular science book at that price. But to my great surprise, it's nearly sold out, and Oxford University Press brought out a paperback, which is being sold in India at a special price of 695 rupees. So if you want to know more about this subject, then you can look at my book. So with that, I shall end here, and I don't know whether to allow them to ask questions.
So let's thank our professor for the wonderful talk. Maybe 3-4 questions we can take. So first come, first serve basis. If you have questions, please raise your hand. Go on.
Sir, why there was a gap for 50 years in the beginning?
Okay, so that's a very important question. Again, I did not have time to get into that. So then for that, to answer that question, I also have to get into the theory of, I explained only one aspect of dynamo theory, how toroidal field gets produced from the poloidal field. The other aspect is that from toroidal field, one has to generate poloidal field. So how that happened, so there are some random fluctuations in that process. So out of that, we have been able to construct a theory of this sort of thing are called grand minima. So I may mention that that a paper by ours was, we developed this theory, and the sign means that that paper was accepted as, selected as editor's suggestion in physical review letters, which is one of the highest honors for a physics paper. Anyway, so beyond that, I don't have, it's not possible to go into more detail, but basically there are some fluctuations involved in the process of generation of poloidal field from the toroidal field, and that is crucial for producing these irregularities.
So next question. Go on.
Hello. Yes. What kind of effect does temperature have on the different kinds of magnetic field which you spoke of?
Effect of temperature?
Yes.
Well, I would say put it the other way around. So what sort of effects magnetic field produces on the temperature? So I mentioned that in these ideas of magnetoconvection, that in the region where the magnetic field is concentrated, in that region, because the tension of the magnetic field, convection cannot take place effectively, and that's why in that region temperature is reduced, and we believe that is the reason why the sunspots appear darker, because the temperature is reduced because of the strong magnetic field. Heat transport of, in the form of convection is suppressed in this region.
So last question. Go ahead.
Does the study of these sunspots lead to some predictability in coronal mass ejections?
Okay, yeah, that is also a very important question. So when you are talking about prediction, there are two kinds of prediction. One is long-term prediction, and another is short-term prediction. So long-term prediction is the like that, whether the next, I think, cycle, what will be the nature of the next sunspot cycle 11 years from now, or whether it will be a weak or strong. So that is a long-term prediction. And the short-term prediction is that question whether is there going to be a coronal mass ejection from 3-4 days from now. So there is quite a lot of research going on, both these subjects, I think, long-term prediction and short-term prediction. So I may mention that from our group, we are very much involved in the long-term prediction, and I think before the present cycle, which is called cycle 24, from our group, we made a prediction before the cycle started. I think I have it in one of the slides. So I think around this time, before the present cycle, which is called cycle 24, started, from this, around this time, two theoretical predictions were made by two groups based on solar dynamo model. So this was a prediction where the cycle, where the peak of this cycle would be according to our rival group, and this was our prediction. So in the history of this subject, this is the first time some group was able to make a theoretical prediction before the beginning of the cycle about what would be the nature of the cycle. So quite a lot of research nowadays going on, both for this long-term prediction and short-term prediction.
Okay, let's thanks Professor Rai Choudhary once again.